Hello and welcome to our next module on Reed-Solomon codes. Let's start with a brief outline of today's talk. We would understand what we mean by Reed-Solomon codes. Then we will look at the encoding for Reed-Solomon codes. We will realize that Reed-Solomon codes are very amenable to hardware implementation. We will look at how to do it efficiently using hardware. Then we will look at how they perform over real channels, and finally we will spend some time on nested codes. So, let us see what we have done so far. We have been looking at the general class of BCH codes, where we have started with the primitive polynomial, looked at the extension fields, the notion of minimal polynomials, generator polynomials, and then finally the BCH codes. Now, if you look at where we are in terms of Reed-Solomon codes, we clearly understand that Reed-Solomon codes are a subclass of BCH codes. We pointed it out in the earlier lecture that the umbrella code is the linear block code, cyclic codes form a subclass of linear block codes, BCH are special subclass of cyclic codes, and finally we are going to study Reed-Solomon codes. So, they are an important subset of non-binary BCH codes. We will realize shortly that there is no point in forming binary Reed-Solomon codes, they will have no meaning. We will look at effective non-binary BCH codes. And the applications are at many places, including lot of storage devices using CDs, DVDs, barcodes, they all use Reed-Solomon codes. Because of its burst error correcting capability. Wireless channels and mobile communications also employ Reed-Solomon codes, so do satellite communication and deep space communications, including we have this digital TV and digital video broadcast DVB standards, and ADSL, XDSL also use some form of Reed-Solomon codes. So, they are present everywhere. There is a very strong class of codes and we are going to understand how they work today. So, what is very important is that the BCH codes with m equal to 1 is the category of Reed-Solomon codes. That is, the extension field GFQ raised by m and GFQ, the sub base field, they are the same. So, the field maps onto itself. So, n, which is the primitive block length, will be q raised by m minus 1, but m happens to be 1, therefore, it is q minus 1. Now, we have already understood from BCH codes that the minimal polynomial of any element b in the same field GFQ is a linear factor like this. Since the symbol field, the subfield, and the error locator field, the extension field are the same, since m is 1, all minimal polynomials are linear. So, it is very easy to find the minimal polynomials for the Reed-Solomon codes, and by that same notion, the generator polynomial g of x is nothing but LCM of f1x, f2x up to f2tx. We have seen this general formulation for BCH codes, but these are nothing but just x minus alpha squared, x minus alpha raised by 2t minus 1 up to x minus alpha 2t. So, we really do not have to work hard to find the minimal polynomials, neither do we have to find the LCM, because none of them repeat, and it is quickly it yields the g of x for Reed-Solomon codes. Now, we are talking about the t error correcting Reed-Solomon codes, and the degree of the generator polynomial we just saw will always be 2 raised by t from this previous example. Please note that there are 2t linear factors. So, all the x's multiply. So, the highest power will be x raised to 2t. So, we also know that for any BCH codes, the highest power of x, the degree of the polynomial g of x is n minus k. Therefore, n minus k equals to 2t, and therefore, we can in general also write g of x as starting with x minus alpha raised power I, not necessarily x raised power alpha raised power 1. It can start from any one and go up to 2t plus I, and this will be the generator polynomial in general for an RS code. Let us look at a quick example. We are interested in finding out a double error correcting Reed-Solomon code. We need the block length, let n be equal to 15, and we need the Galois field GF16. Needless to say, the base field and the extension field is the same, so we have GF16 as the working Galois field. Now, since this is a double error correcting code, we need to specify t equal to 2. Now, we have to construct GF16, so we can use this primitive polynomial to construct it, and GX can be written as the linear factors. Now, t is 2, so 2t is 4, so we have x minus alpha, x minus alpha squared multiplied with x minus alpha cubed multiplied with x minus alpha raised to power 4, and this should yield to us the g of x. So, we can write it out in terms of alpha and alpha powers, and therefore, this is x raised to power 4 plus alpha raised to power 13 x cubed plus alpha raised to power 6 x squared plus alpha raised to power 3 x plus alpha raised to power 10. This is the generator polynomial for a double error correcting Reed-Solomon code. So, if you look at this generator polynomial, we make the following observation, that this encoding procedure will take 11 symbols. Why? Because it is a 15,11 code. 15,11, see, n minus k is the highest power of g of x, n minus 4 is n minus k is 4, n was specified to be 15, consequently we obtained k is equal to 11. So, it takes in 11 symbols, and this tantamounts to 44 bits, because there are 4 bits per symbol, because we are working over GF16. So, this encoder takes in 44 bits, equivalently 11 symbols, and converts them into 15 symbols, which is equal to 60 bits. Okay. So, let us look at some of the properties of Reed-Solomon codes. First and foremost to observe is that Reed-Solomon code are maximum distance separable codes. So, they are really good codes. Let us understand this. So, we claim that Reed-Solomon code is an MDS code, and the minimum distance is n minus k plus 1. So, d star equals to n minus k plus 1. How do we prove that? So, let us say the design distance of the Reed-Solomon code d is equal to 2t plus 1. Because you know BCH codes are designer codes, we can start with the design distance that we want to make it for. So, d star should be greater than or equal to the design distance 2t plus 1. But you know that for Reed-Solomon code, the highest degree is 2t for g of x, which should be equal to n minus k. That is by the general understanding of cyclic codes, and Reed-Solomon code forms a subclass of cyclic codes. Consequently, d is equal to 2t plus 1 should be equal to n minus k plus 1, because 2t is nothing but n minus k. But we have the singleton bound, which says that d star should be less than or equal to n minus k plus 1. That is the singleton bound. Here we have d star should be coming out to be greater than or equal to n minus k plus 1. Here d star is necessarily should be equal to n minus k plus 1. So, from these two conditions, the only possible solution is d star is equal to n minus k plus 1. So, therefore, MDS code, which requires d star to be n minus k plus 1, is the requirement that is satisfied, and Reed-Solomon codes are MDS codes. So, in general, they are very good codes. So, what does this maximum distance separable code mean? Intuitively, it says the code words are as far possible as possible algebraically in the code space. That is the maximum distance separable. You can't separate them out anymore. And this also implies that there is some kind of a uniform word distribution in the code space. Now, we must observe one thing is that for a given minimum distance, in order to have a high code rate, one must work with larger Galois fields. We will soon see this when we go to a table of all good Reed-Solomon codes, and we will see how the code rate plays a role with respect to the error correcting capability. So, let us look at some typical Reed-Solomon code parameters. We have here q is equal to 2 raised power m. So, this is the Galois field over which we are working. So, we start with non-binary. So, gf 2 raised power 2, gf 2 raised power 3, and so on and so forth. So, I have taken up to 256, but we can keep going. We have n values, so you specify the n. Now, once you specify the n and the Galois field over which we work, then what we have to do is specify the number of errors you need to correct. So, next comes the specification of t. The moment you specify n and t for any Galois field, rest of the job is mechanical, because just take the linear factors and multiply them out. How many linear factors? 2t. So, in the first case, you are now getting k equal to 1 and the d star is equal to 3, and the code rate is 1 by 3, because you can see that k is equal to 1 and n is equal to 3. But you can go to higher and higher Galois fields, and for example, the moment you go to n is equal to 7, but you are in working over gf8, you get immediately 1, 2 or even 3 error correcting codes are possible, okay, because you need to have those many linear factors. Subsequently, if you go to gf16, you can have up to 7 error correcting codes. 7 errors can be corrected in one code word. But what we can do is make some basic observations. Let us separate the first of all the different Galois fields and then make an observation. So, the best in the class code rate is, if you can see, improves from 0.33 going up to 0.86 for Galois field gf16, up to 0.93, 32 and up to 256.96. So, we are going closer and closer to 1. We are getting very efficient code efficiency simply because we are going to higher and higher Galois field. But within that same class, so if you are looking at gf256, we can have 5, 15 or even 50 error correcting codes, but you can see that the code rate would drop subsequently. But you have enough possibilities to have very efficient codes here. Let us look at another thing. Suppose we are interested in only 5 errors being corrected per code word. So, we have gf16 5, but the code rate is 0.33. You have got gf32, again t is 5, so we have 0.67. Again for 256, t error correcting code t equal to 5, but the efficiency is 0.96. So, you can see a pattern, you can have much more. So, invariably any useful practical Reed-Solomon codes are above gf256 or even higher in real life. Let us look at an example of a Reed-Solomon 255, 223. This is a popular Reed-Solomon code with 8-bit symbols. So, each symbol is 1 byte and the Galois field is gf255. So, what it means is it takes in 223 bytes of data, pads up with 32 parity bytes, and then it yields 256 byte long code word. Okay. So, n minus k is 32. So, 2t is 32 or t is 16. So, we worked it out the other way around, and so immediately by looking at R is 255 comma 223, I can, just looking at this n comma k, I can predict that t is equal to 16. So, it can correct 16 errors, right, but these are 16 symbol random errors. So, consequently, this code can correct up to 16 bytes anywhere in the code word. So, this is pretty strong. So, how strong really are Reed-Solomon codes? That is the question we need to ask ourselves. So, they are definitely an extremely pronounced effect on the efficiency of a digital communication channel because of their strong error correcting capability. So, let us take a very simple calculation, back of the envelope calculation. Suppose we have a operation which is transmitting 1 million bytes per second. Okay. So, this is a data rate of a high speed communication link. So, approximately we have about 4000 blocks of 255 bytes each per second. Okay. So, this if you multiply them, it is roughly of the order of 1 million bytes per second. So, we have consequently 4000 blocks of 255 bits. So, these are code words. So, 4000 code words per second are being sent, right. Now, suppose 1000 random short errors less than 17 bits in length per second are injected into the channel. This is just an example. So, about 600 to 800 blocks per second would be corrupted, right. So, this, if this was not protected, then all the blocks or most of the blocks would require retransmission. Okay. But let us suppose we want to apply Reed-Solomon codes, right. Then what we do it, for every 235 bytes we pad them up and we get this 255 byte long code words, and so we are padding up with 20 parity bytes. If you employ this and look at the error correcting and detecting capability, we would see that retransmission will not be required for 800 years at the rate of 1 million bytes per second. That is how strong it is, and that is just the part of the story. And this RS code will also make errors in detection, but the mean time between incorrectly decoded blocks will be over 20 billion years. So, in a real practical world, this application of this 255 comma 235 code practically makes it a very, very useful, almost error free communication, even working at this high rate of 1 million bytes per second. And this efficiency is also not too bad. Of course, we can improve the efficiency, the code rate of this code by going to higher Galois fields. So, the point is that Reed-Solomon codes are very strong practical codes. Now, let us look at the encoder representations, and we would like to encode the following generator polynomial. So, this is the epsilon g naught g1 g2 up to dot g2t minus 1 up to this monic x raised by 2t. So, please note we have arranged it so that the highest power of x is to the right. This is a very easily implementable form in hardware. So, how does the hardware encoder for Reed-Solomon look like? So, please note there is a shift register, there are some coefficients which will pump in the values for g of x, and then you have two switches, switch 1 and switch 2. And the way it will work is first there will be k clock cycles, wherein this will be a systematic codes, which consequently means that the input data goes directly to the output. So, please note it is hardware. So, for every time I clock in the input, it goes out. So, the first k symbols are the same because it is systematic. The rest n minus k symbols, I will close these switches and get the encoded version which is multiplied with g of x. So, if you look at the steps, switch 1 is closed using the first k clock cycles to allow the shifting of the message, right. n minus k shift registers. Now, this k cycles, the contents of the shift register and the feedback loop is continuously changing based on the information symbols being shifted in, as well as the addition prior to each elements of the shift register. Okay. So, what has happened is the switch 1 is closed and switch 2 is connected here. So, by the time this data is being clocked, please note this values of the shift registers are also continually changing. Now, the switch 2 is down for the first case clock cycles, allowing the simultaneous transfer of the message symbol directly into the output register, leading to the systematic Reed-Solomon code. Okay. After the transfer of the kth message symbol to the output register, switch 1 is opened and switch 2 is moved to the up position. So, what we do is after this k symbol, switch 2 is moved to the up position, because we would like to read out what is present in this shift register, right, and this one is opened. So, no more further changes will be happening. So, what is residing in the shift register elements are actually the parity symbols. These symbols are ready to be shifted out and appended to the information symbols already stored in a buffer, which will create the entire code word. So, please note the very efficient hardware implementation, first k clock cycles and second k clock cycles, things happening in parallel, right. So, during the remaining n minus k clock cycles, we clear the parity symbols contained in the shift register by moving them to the output register, and we are ready to encode the next code word. So, the total number of clock cycles is equal to n, and the contents of the output registers are actually the final code word polynomial corresponding to the k information symbols. So, let us look at a very simple example. This is from a standard IEEE 802.15.4a standard. It is an RSA 63,55 encoder. So, it can be very easily implemented on an FPGA. So, here n minus k is 63 minus 55 equal to 8 is equal to 2t. Consequently, it is a 4 symbol error correcting code. So, we multiply it out very easily, x minus alpha squared, so on and so forth, up to x minus alpha raised to 2t. 2t happens to be 8. So, we have this 8 linear factors, multiply it out, and immediately you have the g of x, and the corresponding shift register portion of the hardware encoder is given here. These are the coefficients of your g of x. So, this is a simple example how we can include in our RS encoder this notion of this generator polynomial. Now, we come to the question of real channels. How do they perform over real channels? So, a word of caution, one may be tempted to believe that as we decrease the code rate of a Reed-Solomon code, the BR performance would improve monotonically, because you would believe that you're padding in extra bits, there are overhead bits, hopefully your BR performance would improve. However, in real world communication, the modulation scheme also plays a role with respect to BER. Thus, both modulation and coding mechanisms have to be considered. So, we are now touching base with reality. Just because you have encoded symbols using a Reed-Solomon encoder, or for that matter any encoder, it does not mean that your bit error rate will keep going down if you increase the redundancy. We must consider the modulation part. So, you have to know that one of the mechanisms improves the error performance, while the other would work to degrade it. So, modulation, we have the higher modulation scheme would cause more errors to happen, and this addition of additional parity bits reduces the BER. So, they are working opposite to each other. So, let us see the improving mechanism is coding. The greater the redundancy, the greater will be the error correcting capability of the code. But if you pack in too many redundancy, you have to switch to higher modulation schemes, which will make it counterproductive. So, let us make some observation that the degrading mechanism is the energy reduction per channel symbol compared to the data symbol that results from increased redundancy and faster signaling in a real time communication system. So, your energy per symbol also degrades. The reduced symbol energy causes demodulator to make errors. Okay. So, just packing in additional bits, padding it with additional parity bits would overall reduce the symbol per the energy symbol and causing it to have a poorer performance. So, there is a trade off, and somewhere there will be an optimal solution, and before which the second mechanism wins out and very low rate codes would again have poor performance. So, there is a trade off mechanism happening. Let us look at this. So, if you look at this curve, on the x axis we have the code rate, okay, the efficiency of the code, and on the y axis we have the energy per symbol EB over N naught. So, it is the normalized SNR, and we are looking at a typical error rate of 10 to the minus 5. So, what does it take to achieve this PB equal to 10 to the minus 5? And if you look at, we are looking at Reed-Solomon 31, K code. So, if you change the K, your code rate changes. So, by changing the different values of K for this Reed-Solomon 31, K, I move along the x axis, okay, and we can eventually compute EB over N naught and plot these performances over different kinds of channels. So, we have a Gaussian channel, we have a Rician channel, we have a Rayleigh channel. These two are fading channels. Rician channel when you have a direct line of sight, Rayleigh channel when you do not have a direct line of sight from the transmitter to the receiver, and Gaussian channel, as you know, is a standard AWGN channel. So, if you just consider the Gaussian channel, the optimal point where you have the minimum EB over N naught, because your performance if measured in terms of PB, right, is 10 to the minus 5. So, all these curves are for the same performance level, but here you require the minimum EB over N naught. Energy is the minimum SNR requirement for this code rate. If you go beyond that, again you have to pump in more energy per symbol. Okay. So, all of them go through a minimum. So, this is an important observation from a real world channel. Earlier we would have believed that as the code rate goes down, your performance would necessarily increase with the EB over N naught. Now, let us spend some time from the energy perspective. Today, energy is essential in the design aspect of all communication systems, be it from the green telecom perspective, increased battery life or better performance. Energy consumption by communication system is an interesting and important design constraint. If you look at situations like wireless sensor networks, where we are necessarily limited by the energy available, we must take it into consideration. Now, if you consider the hardware implementation of the error control encoding block and the modulator block, the energy expended can be categorized as follows. There is a computational energy for channel encoding and decoding. This is important. So far, we just believe that multiplying over various Galois fields, adding, doing all that computation requires negligible energy. Well, that may not be true. You could possibly end up spending a lot of energy just doing the computation, encoding and decoding. I mean, it is possible that you are spending more energy encoding and decoding than saving in terms of getting that same bit error rate. Then there is a circuit energy required for modulation and demodulation, and then you have the signal energy, the radio energy, which is actually used for transmitting all of those bits, including the redundant bits. So, at short distances, the energy consumed in the transmitter circuitry and computation is comparable to the signal energy. Why? Because the required radio energy, the actual energy for the electromagnetic radiation is very small, and it becomes comparable to what we spend inside the circuit in terms of the circuit energy and the computational energy. So, the overall design objective should be to minimize the total energy, including computational energy, circuit energy and the radio energy. If you take all of them together and maximize the performance or minimize the total energy, then we have an energy perspective to the whole thing. So, we have to make sure that for a particular coding and modulation configuration, we have to optimize the energy consumption. So, the optimal pair of energy of coding and modulation will also depend on the distance between the transmitter and receiver. Why is that? Because the radio energy depends on the distance between the transmitter and receiver. So, let us look at this example. This is an example using a Reed-Solomon 31, K code. So, K can be changed and thereby changing the error correcting capability. So, in this graph you have on the x axis the error correction capability T, and the y axis the total energy per data bit in microjoules. Now, we have by these different shades that the different components. What are the components of energy? The computation energy, the circuit energy and the signal energy, which is the radio energy. So, the darkest is the signal energy, followed by the circuit energy, the lightest is the computation energy. So, if you see that the total dark line is the total energy. So, there are different components there, and as we increase the error correcting capability, all of them increase, consequently leading to an increased total energy per data bit in terms of microjoules. Now, if you look at it from another perspective, suppose on this axis you have the code word length, on this axis you have the error correcting capability, and on the z axis you have the total energy per data bit in terms of the microjoules. Okay. So, we are plotting the total energy versus the code word length and the error correcting capability together. So, you can get a feel that, for example, the optimal energy comes for here for RS 127, 121. So, it is not obvious just by looking at the N and K of a Reed-Solomon code what is the best Reed-Solomon code to pick. It is not just the error correcting capability, because in an earlier table we had plotted with respect to the error correcting capability T. That table is not itself sufficient if you are considering the energy perspective. You have to look at the other aspects of the energy as well. Now, we come to the notion of nested codes. Okay. So, one of the ways to achieve codes with large block lengths is to nest codes. What do we mean by that? In this technique, we combine a code of small alphabet size and a code of a larger alphabet size. So, we are combining two codes and nest them. We will have a notion of an inner code and an outer code. So, let a block of query symbols be of the length small k, capital K. So, K is the length of a block. Now, these two K's would correspond to the two different codes, one with a small alphabet size and one with a large alphabet size. So, you can write this as K subblocks, capital K subblocks of small k symbols, making it K into capital K symbols altogether. Okay. So, each sub block can be viewed as an element of a q is per k alphabet. All right. So, a sequence of capital K such sub blocks can be further encoded with a capital N comma capital K code over GFQK. Alright. So, we are doing a two-step process. Now, each of the N Q S K query symbols can be viewed as a K query symbols that can be encoded with an N comma K query code. So, therefore, you are nesting it out. So, the nested code has two distinct levels of coding. So, it is coding over coding. So, let us look at how we are trying to do it. At the center of it is the query channel. So, you have a notion of the inner code. What does the inner encoder do? It takes N comma K code over GFQ. So, it takes K symbols and converts it into N symbols. And then this guy is encoded further using this NK code. So, together this is the outer code and inner code form the nested code. You have to reverse the process on the decoding side. So, you have an inner decoder which decodes at small n comma small k code, and then there is an outer decoder which decodes capital N comma capital K codes. So, you have a coding over coding, and this is also used in practice. So, let us look at some examples. So, suppose we have an inner code, the RS7,3 double error correcting code over GF8, okay, and we have an outer code, the Reed-Solomon 511,505 triple error correcting code over GF8 raised to power 3. So, if you nest these codes, okay, so this is a small k 3, this is a capital K 505. So, small k into capital K should be 1515. So, the nesting code, the super code is 3577, 1515 code over GF8. Now, is it good? Well, this code can correct any random pattern of 11 errors, okay, and the code word is 3577 symbol long. And what is the symbol? Symbol is an element of GF8. So, this is a simple example of nesting RS7,3 with RS511,505, leading us to a big nested code of 3577, 1515 code over GF8. So, now let us summarize what we have done so far. We introduced in this lecture the concept of Reed-Solomon codes, which is a subclass of BCH codes. We looked at the encoding procedure. Specifically, we looked at the hardware implementation. It is very easy to encode Reed-Solomon codes using shift registers and 2 switches. Then we moved on to real channels and the performance over real channels for Reed-Solomon codes. We also considered the importance of overall energy optimization while designing the error control codes, and finally we talked about nested codes. With that, we come to the end of this lecture.